measure.
I sent that thing to Lee for, you know what her office is?
I just did it email-wise.
Chapter
They
28, Section 9.
They didn't have the spring for 2013. But it said they just put that there in their email while I did that, and they sent a letter saying, oh, wait, no. It's like that. I'm trying to work it. I just don't know who that lady is or how I get hold of her or where to find her.
A Fourier, what we have is we have some function f of x. So f of x could be 1, for example, and or whatever it might be. And then we find the Fourier series, and f of x is going to be some constant, a0. You could think of that as the DC component of the signal, plus a1 cosine x, plus a2 cosine 2x, plus blah, 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 a n cosine nx, plus b1 sine x, plus b2 sine 2x, plus blah, 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 bn sine nx on to infinity. Normally we only need about 10 of these guys to get the signal back. So I don't need to have an infinite number of A's and B's in order to do it. I can generate the signal on the other side with just a few of them. Now, if I have a signal that's repeating itself every 2 pi, so I have something that's doing that, then my A0 becomes 1 over 2 pi integral 0 to 2 pi f of x dx. And my an becomes 1 over pi integral 0 to 2 pi of f of x cosine x dx. And bn becomes 1 over pi integral 0 to 2 pi f of x sine x dx. And there's an n sitting in front of that x. And with a little bit of luck, we'll have some signal where all the A's are 0 or all the B's are 0, and it cuts down the computation. Otherwise, you end up having to do all those computations. And you sort of hope that the function's a simple function so that it's easier to do. So if I take the function that I have and I say f of x, so I got a function f of x is 1, then a0 becomes 1 over 2 pi integral 0 to 2 pi of 1 dx, which becomes 1. Does it not? Skipping a lot of steps. 1 over 2 pi x evaluated at 0 and 2 pi 1 over 2 pi times 2 pi minus 0 is 1. So I put those steps in, so that'd be okay. Now we could calculate it as A1 and then calculate A2 and then A3. Or we could just calculate an AN and say AN is 1 over pi integral 0 to 2 pi 1 times cosine n x dx. And then we could have 1 over pi. The integral of cosine would be sine, right? Yeah, so it'd be sine. Yeah. So it'd be sine nx over n evaluated at 0 and 2 pi. Well, sine n's a whole integer thingy, so that's going to be at 2 pi, sine is 0, and at 0 pi is 0, and whatever the n is, it's still going to be 0. So this is going to be 0, so a0 is equal to 0 for all n. That's a for all sign, in case anybody is wanting to know that. And then we could calculate Bn, 1 over pi, integral 0 to 2 pi, 1 times cosine, I already did 1 times cosine, didn't I? 1 times sine nx dx. Okay, so we have 1 over pi. The integral of sine would be minus cosine, so it would be minus cosine nx divided by n, evaluated at 0 and 2 pi. Well, at 2 pi, alright, so now we're going to have to 1 over pi minus cosine 2n pi divided by n minus cosine 0 over n. Well, cosine 0, that becomes a 1, right? So I got 1 over pi minus cosine 2n pi over n minus plus 1. Okay, so if n, so this is b, right? b n is going to be 1 over pi. It's going to be for n odd. Okay, so if n is odd, that's going to make this even. So that's going to be a 1. And that's going to be a, so I'd have a minus 1 over n plus 1. And if n is even, I'm going to have the same thing. I'm going to have the same thing both ways. Okay, so now I've got a b1 is equal to 0. I got a b2 is equal to 1 over 2 pi. I got a b3, so it'd be 1 over 3, so it'd be 2/3 1 over pi. b4, that'd be a quarter, that'd be 3/4, 3/4 pi. And then I would go on, and then I said, well, f of x would be 1 plus. Now the b's are the sine guys, so 1 over 2 pi sine 2x plus 2 over 3 pi sine 3x plus 3 over 4 pi sine 4x plus blah 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 blah. We could have other ones too. Okay, now at f of 0, I end up these guys being 0, and it goes away. Okay, good enough? So that was a silly example because we didn't have to do that. We have to do something else. Now, what happens if I don't do a function out to that repeats itself? These are only good for repeating functions, in case you're wondering. And so that 1 is really a repeating function that would be, so f of x is equal to 1 is something that really looks like this, going out to 2 pi, 4 pi, 6 pi, as I repeat itself every 2 pi or whatever. That didn't make any sense. Forget that idea. I think it's just what it is, 1. And now, if we have something that repeats itself differently, so instead of having a function that repeats itself at 2 pi, we have a thing that repeats itself at 6. So we go to 6, and then we go to 12. So instead of repeating every 2 pi, we're repeating it something else, and we call that L. So the L in this case would be 6. And we come up with, on page 989, A0 is equal to 1 over 2L, integral minus L to plus L, f of x dx. And A1 is equal to 1 over L, integral minus L to L, f of x cosine n pi x over L. And my b's become 1 over L, integral minus L to L, f of x sine n pi x over L dx. And then my function, when I get done, is going to be A0 plus, and this is on page 990, A1 cosine pi x over L plus A2 cosine 2 pi x over L plus blah 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 an cosine 2 n pi x over L. It doesn't look much like an L. It doesn't look much like a n. Plus blah blah blah. Plus the b's, b1 sine pi x over L plus b2 sine 2 pi x over L plus blah 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 bn sine n pi x over L plus continue on forever. So we could have those two situations, both of which existed on the comprehensive exam I had at UNO for my master's degree in math. Luckily I had my Tech Math book with me, otherwise I'd be hosed. I wouldn't be able to solve them easily. But with it, it was quite easy. Alright, so back to what we're doing, 1, 9, and 15. Now why do you think we only have 3 problems to do?
Very long.
Because each of them takes all day. And that's about it, yes. So our first one, f of x is equal to minus x from 0 to 2 pi, and that would be our repeating function. So we need an a0, 1 over 2 pi, integral 0 to 2 pi, minus x dx. Now, we'll look at this guy for a moment, and what does he look like? Well, at 0, I'm 0, right? And when I get out to 2 pi, I'm going to be at minus 2 pi. So this is a triangular function that does that. All right. Now, this is A0 should be the DC component, right? So what's the DC component of a half of 2 pi squared? So this is a 2 pi squared area, and half of it would be 2 pi squared. So I better get that as my answer for this integral, otherwise I'm going to be not happy. But I'm not going to go back and find my mistake if I don't get it. I just won't be happy. Which doesn't really matter if I'm happy or not, right? 1 over 2 pi. And that's minus x squared over 2, evaluated at 0 and 2 pi. So I'm going to have 1 over 2 pi minus 2 pi squared minus a 0, so that goes away. It looks like this is going to be 2 pi. And why it's not 2 pi squared, I don't know, but we'll let that be. So A0 is going to be 2 pi. And then we're going to look at A, N. Normally what I do is calculate A1, A2, A3, A4, and then figure out what AN is later, but we're going to skip those steps and go right to AN. 1 over pi, integral 0 to 2 pi, minus x is a cosine, and x. And because I do this all of once a year, we don't do Fourier transforms in the differential equation class. It's the only class at Iowa Western where we actually do them. Okay, so that's good. I'm going to bring the minus sign out. Minus 1 over pi, integral 0 to 2 pi, x cosine nx. What we'll do is we'll do an integration by parts. And we'll say, if I take uv and I take its derivative, then I'm going to have, it doesn't look like uv, does it? Oh well, can't have everything. uv, then I'd have uv prime minus plus vu prime. Okay, so if I had vu prime, that would equal to uv prime minus uv prime. And if I took the integral of everything, I'd have the integral of vu prime is equal to uv minus the integral of uv prime. Okay, so I have an integral that I can't solve in my head, and I say, okay, well, that being the case, this x guy is going to be v. So v is equal to x, and u prime is going to equal to cosine nx, and v prime is going to be 1, and u is going to be sine nx over n. Okay, so now I come back and say an is equal to minus 1 over pi, and this is the integral I'm now solving, but I'm doing it using this, and so u is sine nx over n times v, which is x, and that's evaluated at 0 and 2 pi, even though it's not saying so here, it really is. And then I've got minus the integral 0 to 2 pi of u, which is sine nx over n, times v prime, which is 1 dx. All right, I got an minus 1 over pi. I've got a 2 pi. When I put the 2 pi in there in the sign guy, I get 0. When I put 0 in there, I get a 0. So that first term goes away. The second term is going to be minus, the integral of sine is minus cosine. Cosine nx over n squared, evaluated at 0 and 2 pi. Alright, well that minus sign goes away, this minus sign goes away. An becomes minus 1 over pi. When I put the 2 pi in there in front of the n, that's going to be a 1. So 2 pi is 1, 4 pi is 1, 6 pi is 1. It's always going to be 1. So that's going to be 1 over n squared minus, I put a 0 in there, and it's always going to be 1 over n squared. So that being the case, an is 0 for all n. Isn't that lovely? And it'd be nice to know if I was right, but we don't so far. We just assume that it is because it's got to be an easy problem, right? All right, so now we're going to look at it bn 1 over pi integral 0 to 2 pi minus x sine nx dx. All right, so that's what we have. Okay. Well, it must be so. Okay, so back to what we're doing before. We're gonna bring out the minus sign. We're gonna have v be equal to x and v prime equal to 1, and we'll have u prime equal to sine nx and u equal to minus cosine nx over n. Alright, so this becomes 1 over pi, the minus sign comes out. I have uv, so that'd be minus x cosine nx over n, evaluated at 0 and 2 pi, minus the integral 0 to 2 pi of 1 u. Now move up here. 1u, okay. U minus cosine nx over n dx. All right, well, 1 minus 1 over pi. I put 2 pi in here. Did I do that right up there? When I put 2 pi in here, I get 0. Okay. And then I get 0 again. Okay, so when I put 2 pi in here, I get minus 2 pi. The cosine of nx pi, 2 pi, is going to be 1. And I'm going to divide it by n. When I put 0 in here, I get 0. So that term goes away. Okay, then I'm going to have a plus. Minus minus becomes a plus. The integral of cosine becomes sine. Sine nx over n squared, evaluated at 0 and 2 pi. Okay, so this guy is going to be 0, because when I put a 2 pi in there, sine of something pi is going to be 0. When I put a 0 in there, it's going to be 0. So I'm going to have bn equal 2 over n. Okay, so I'm going to have, so at that point, we'll look in the back of the book, see how much smoke we're blowing, see whether or not we're even close. It doesn't matter, we're going to go on either way, right? Let's see. Chapter 28, chapter 28:9. And number 1 says minus pi plus 2 times sine plus 1 times sine plus 3 whatever sine. All right, so when n is 1, I get a 2. When n is 2, I get a 1. When n is 3, I get 3 over 2. So that's correct. My bn's are correct. And no matter what I get for an, a0. A0, I should have a minus pi.
That's what I got in the calculator.
Yeah, I should have had a minus pi.
You got 2 pi.
Minus, yeah, should have a minus 2 pi. So I'm missing the minus sign, which is sitting right here that I forgot about, minus 2 pi. And the book is wrong for that guy, because it can't be, minus 2 pi would be correct, I think. All right. Excellent. So anyway, got number 1 right. That's the bottom line. Because B1 is 2, B2 is 1, B3 is 2 over 3, and that's exactly what the back of the book has. All right, moving on. What's the next one we do? Number 9. Now, the other way you'd do that problem is you'd find the table for the integral of x sine x and x cosine x, right? And thank you, author. It's not in the back cover of your book. But if I look at page 986, I see that the integral of u sine u du is sine u minus u cosine u plus c. So there is an appendix, E, in the back of the book that has a better set of integration tables. So I didn't necessarily have to use integration by parts on the last program, on the last guy. I could have gone to a better set of integration tables. Okay, so number 9, f of x is equal to 0 from minus 5 to 0, and is equal to 6 from 0 to 5. Okay, so I got a situation where I have an L is equal to 5. I want A0 going to be integral minus L to L of f of x. And so that's going to be integral minus 5 to 0 of 0. We can figure that one out pretty quick. And from 0 to 5 of 6. So the first guy is 0. The second guy is 6x evaluated at 0 and 5, which would be 30. So I end up with 30. Now, what I said was A0 is supposed to be the DC component of the signal, right? So I go back and I have something that's 0 here. It comes up to 6 there, stays at 6 until I get here. At 5. What's 5 times 6?
30.
30. All right. So it looks like I got twice the DC component, but I won't worry about it. All right. So unless wait a minute. This is supposed to be times what? 1 over 2L. So this has to be 1 over 12. 1 over 12. Divided by 12, divided by 12. 15 over 4. Number 9. Three. 15 over 4. Wait a 2. What the heck is 30 over 12 anyway? 2.5. Now, why does the book say it's 3? Oh, they couldn't have. See, I was thinking that it would be 30. Yeah, it should be. It should be 30 divided by 10, which is 3. So, why don't I have 3? Oh, I know why I don't have 3. What's 2 times L?
3 times 5.
Yeah, what's 2 times 5?
12.
That's not 12. Very good. So if this is a 10 and that's a 10 and this is a 10 and that's a 10 and that's a 10, then I end up with this being 3, and life is so much better. And that's what my DC component should have been 3. By looking at it, it is 3. Life is now better. All right, now I'm looking for A, N. So I'm on page 989, and I'm looking for 1 over L, which is now 5, integral from minus L to L of the function f of x times cosine n pi x over 5 dx. Okay, so that's what I'm doing. And so 1 over 5. When I go integral minus 5 to 0 of 0, I'm going to get 0. So that's good. Plus integral 0 to 5 of 6 cosine n pi x over 5 dx. So that's what I'm doing. The integral of cosine is going to be sine. So this is going to be 6 sine n pi x over 5 divided by n pi over 5, evaluated at 0 and 5. Well, the sine of 0 is 0, and the sine of any multiple of pi x over 5 is not 0. Yes, it is. When I put the 5 in, the 5 goes away on the bottom, and then pi x, no, pi doesn't do that. The 5 goes in here, and this is n pi, any multiple of pi, sine of it is 0. So this whole thing is 0. So a n is 0 for all n. And then we'll look for b n. 1 over L, integral minus L to L, 6 cosine n pi x over L, which is 5, dx. Darn. Not really. This was cosine. This is sine. All right. So now I'm going to have 1 over 5, integral minus 5 to 5, the 0 of 0, which becomes 0, plus integral 0 to 5 of 6 sine n pi x over 5 dx. 1 over 5. The integral of sine is going to be minus cosine. So it's going to be minus 6 cosine n pi x over 5 divided by n pi over 5, evaluated at 0 and 5. All right. I got minus 6 over n pi. Minus 6 over n pi. And when I put a 5 in here, I get put a 5 in there. The 5 goes away, and I get cosine n pi. Cosine n pi so that's going to be minus 1 raised to the n. Okay, because when n is odd, cosine n pi would be minus 1. When n is even, cosine n pi would be 1. Okay, and then I'd have minus, when I put a 0 in there, the cosine of 0 is 1, I would have a 1. Okay, so I got Bn is going to be equal to minus 6 over n pi for all n even. No. When it's even, it's 0. So it's going to be 0. And Bn is going to be, when this is odd, I'm going to have minus 1 minus another 1 from minus 2. I'm going to have 12 over n pi for all n odd. Okay, so B1 should be 12 over pi. B2 is equal to 0. B3 is 4 over pi. B4 is equal to 0. B5, 12 over 5 pi. All right, now it's time to look in the back of the book. Number 9, I got a 3, and I have the sine guys. Okay, the sine guys are the b's. Yeah, the sine guys are the b's, and I have 12 over pi, and then I got 4 over pi, and then I got 12 over 5 pi. Yeah, and looks like I'm there. Okay, so 2 out of 2. 2 out of 2. There's plenty of time left to do the last problem. Disgusting. What are we doing next? 15. Now, why did I always do the even problems, right? Why is it that I'm doing the odd ones here?
Because these are more challenging.
Huh?
Because these are odd.
Because the odd ones have an answer in the back of the book, and I know whether or not I'm right.
Maybe you're suffering from March Madness. That could be too.
Oh, it could be. So I'm doing 15 next? 15. The UConn girls still playing? Yes, okay, well then the tournament's still on.
Rapid girls are still playing too.
So yeah, they are, aren't they? F of x is sine x 0 to pi, and it's 0 pi to x to 2 pi. Okay, so now we don't have to use that L thingy again. Okay, so now I'm going to ask myself, I have something that looks like that all the way to pi. That's going to be my DC component, so that's the average value of it, whatever. Well, too hard. A0, 1 over 2 pi, integral 0 to 2 pi, sine, well, go 0 to pi, sine x dx plus integral pi to 2 pi of 0 dx. That looks good. 1 over 2 pi. The integral of sine is minus cosine. Minus cosine x, evaluated at 0 and pi. And 1 over 2 pi, I put the pi in, and I get a minus 1. So minus a minus 1, and then I put the 0 in, and I have minus. I put the pi in. Minus, minus. Okay, we'll do this. Put that guy there. I got minus, minus 1, minus 1. Okay, so that looks like a minus 2. That looks like a plus 2. That looks like 1 over pi. And what do we say the average value of the sine wave was? I think we said it was 1 over 2 pi. Thinking back to circuit analysis 1. Anyway, yeah, we'll accept that answer. All right, so now I'm looking at AN, 1 over pi, interval 0 to pi, sine x, cosine nx, plus integral 0 to, no, pi to 2 pi of 0 dx. And we'll get to the right page of the book to make sure we're applying this formula right. Okay, we are. All right, so now I need integral of sine x cosine nx. So and I got it on good authority that there's a cool set of integration tables in Appendix E. Okay, so I'm in Appendix E, and I want sine, cosine. All right, I see sine. Okay, there it is, sine, cosine. Okay, number 77. So I'm on page 1170, looking at number 77, and I end up with 1 over pi, and my integral is the cosine of m plus n. Okay, so that'd be the cosine minus the cosine of 3, no, of n plus 1 x divided by 2 times n plus 1 minus the cosine of m minus n minus 1 x divided by 2 n minus 1 evaluated at 0 and pi. Okay, well that's cool. Alright, so this is the cosine component, right? I'd expect it to be 0. So when n is 1, see what happens? Well, when n is 1, I can't use this formula because then I'm dividing by 0. Okay, so I'd have to use a different formula if I was using n is 1. But if n is 2, I put a pi up here. Put a pi there. The cosine of this guy would be either plus or minus 1 depending on what the n is, right? And the cosine of that guy would be plus or minus 1 depending on what the n is. And when I put a 0 in, 0, this would either wipe him out or not wipe him out. Alright, so I got 1 over pi. And when I put the pi in, I'm going to get minus 1 raised to the n plus 1. When n is 1, then this becomes a 2. When that's a 2, then this is a 1. Okay, and that looks good. Divided by 2 n plus 1 minus 1 raised to the n minus 1 over 2 n plus 1 minus, when I put a 0 in, I get a minus 1 2n plus 1 minus 1 over 2n minus 1. Okay, so these are both positive, and the other guys are both negative, are negative or positive. Okay, so what am I calculating here? I'm calculating an. So when an is going to be equal to when n is even. Okay, so if n is even, then this is a minus sign. That becomes a positive sign. And then these guys are both positive signs. So I'm going to have everything added together. I'm going to have 2 of these, and I'm going to have 2 of those. So I'm going to have 1 over n plus 1. I'm pretty sure this is a minus sign sitting there. Plus 1 over n minus 1. When n is equal to something else, when n is odd, okay, so when n is odd, this is odd, that makes it even, that makes these guys negative, those guys positive. It's going to be 0 for n is odd. Okay, now can I leave it that way, or should I call it different? N is equal to, okay, so it'd be n minus 1 plus n plus 1 divided by n squared minus 1. So that'd be 2n over n squared minus 1. Alright, and that calls for a look in the front and the back of the book. See if we're anywhere near being close before we move on. So this is number 15. And okay, so the cosine guys, I have 2 over 3 pi when n is, what happened to my pi? Who took away my pi? All right, back up here. Right here. 1 over pi right there. So I have a 1 over pi sitting there. I have a, well, this guy times pi like that. Okay, so when n is 2, n can't be 1, but when n is 2, I have 4, and I have 3. 4/3 with a pi on the bottom. And 15 says 2 over 3 pi. 2 over 3. I don't see that. Wait a minute, 2 over 3 pi? It would appear that I made a mistake. I want 2 over 3 pi. I got 3 pi there, but I have 2 there. I have 4 there. I have 4 over 3 pi. Oh, bummer. But at least I got the even odd guy right. So that's pretty good. I put 2 pi. This guy's a negative sign, but it doesn't matter. I already compensated for that. I put the zeros in. Okay, I got rid of the 2's when I did that. Yeah, I don't see what I did wrong. Back to calculating the b's. Bn equals 1 over pi integral what? Integral 0 to pi sine x sine nx dx. Okay, so that's good. And then plus integral pi to 2 pi of 0 dx, which becomes 0, and we don't have to worry about it. All right, so now we're going to go and check my integral tables again to find the sine interval guy. There's that, there's D, there's my integral table. So I got sine. All right, well, it's number 75. Number 75, page 1169. All right, I'm going to have 1 over pi okay, n is n and m is 1. So I got sine n plus 1 x divided by 2 n plus 1 plus sine 1 minus n x divided by 2 1 minus n evaluated at 0 and pi. Now it would appear to the casual observer, now why would sine give us sines and cosine give us sines? You notice 75 and 76? Notice something weird about that? Is that weird?
What's wrong?
Yeah, that how can that be? So we're gonna do right now, if I put in pi in these things, I get a 0 out of there, and the back of the book doesn't say I have 0. So we're gonna go and open Maple up and see what Maple thinks about the integral of sine.
Well, one's negative.
One's negative and one's positive?
Yeah. 75's negative.
Yeah. No.
The first one.
So, oh, there's a negative sign there, yeah.
So
Yeah, there is a difference between the two, but it's still, because I'm curious about it. So I want the integral of sine x times sine n x dx. Well, that tells us that is what it is. Alright, well, that being the case, it would appear to the casual observer that Bn is equal to 0 for all n. Because when I put no matter what I do, the sine of pi is going to be 0, and the sine of a multiple of pi is going to be 0. And looks like that's the case. I look in the back of the book in 15, and there is a sine function there. There's a sine x guy saying that he's there. 1/2 sine x. Oh, I know what we have to do. Again, we can't use this guy to come up with n at 0 when n's 1 because we're dividing by 0. So we'd have to go back and calculate a1 separately. So b1, we're going to calculate b1 separately. So b1 is going to be 1 over pi integral 0 to pi sine x squared dx. Plus the guy that's going to be 0, which I'm not writing. I'll write him anyway. 0 pi to 2 pi 0 dx, which is going to be 0. Alright, so now the integral of sine squared thank you very much, author, for giving us the integral of sine squared in the easy place. I gotta go look for it in the harder place. And it's sine to the end, but I don't want sine to the end, I want sine squared. Here it is, sine squared. Number 71, page 1169. Alright, so sine squared is going to be 1 over pi one half x plus 1/4 sine minus 1/4 minus 1/4 sine 2x evaluated at 0 and pi. When I evaluate this at 0, I get 0. When I evaluate it at pi, this guy is 0, that guy's pi over 2. So this guy is going to be 1/2, which checks with the backup book. Okay, very good. We are now done with chapter 28, moving on to the next chapter, which is 29. And we're only a month behind. Is that all? Wow. Well, that shouldn't be much of a bother. Because that's the more difficult thingy. Alright, number 29. 1. Alright, so we're going to solve differential equations, and does it give us a method for doing it? No, it doesn't. Okay, excellent. So we're in section 29.1. Now if I have x squared plus x plus 2, if that's my f of x, what is the degree of the function? The degree of the function is 2, because that's the highest power of x that I have. If I have a function y double prime plus 2y prime plus y is equal to 0, what is the order of the differential equation? The order of the differential equation is 2, because that is my highest derivative. So I talk about the degree of an equation, I talk about the variable raised to some power. When I talk about the order, I'm talking about something different. Alright, so now we're looking at problem number 2. And problem number 2 wants to find the order and the degree. Alright, so I've got y prime squared minus 3x y prime plus 2 is equal to 0. So my order is 1 and my degree is 1. The order is 1 based on the power of the x guy. That's my degree. And then the order is based on the highest derivative. It doesn't matter that I squared it or not. That's irrelevant. Not even going to another piece of paper because these are going to be pathetic. Number 6, we want order and degree of y prime plus x cosine x. And because this is a democracy, we'll have to vote on it. Okay, order. How many vote that the order is 1? 1, 2, 3, 4. Okay, so we have 4 votes. How about degree? Anybody want to tell me what degree is? Degree is... Nobody wants to tell me what the degree is?
0.
The degree is infinite.
Yeah.
Why is the degree infinite? Well, there's a cosine sitting there, right? What's a series expansion of cosine? 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, blah, 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 right? So this is a trick question. You're supposed to do exactly what Patrick's did, which is put a 1 up, right? Because the x has a power of 1 associated with it. But the fact of the matter is the degree of that equation is infinite because there's a cosine function sitting there which would have an infinite degree on the x guy. Alright, so that's just the way it is. And I don't recall whether that, well, every test I make up is different anyway, so there could be a problem if it talks about that. Verify that the solution is an answer. Okay, so that's what we're doing next. And so for 15, we have that y double prime plus 16y is supposed to be 0, and our answer y is c1 sine 4x plus c2 cosine 4x, I think. Alright, and we want to verify that this is the right solution. Okay, so y prime is 4 c1 cosine 4x minus 4 c2 sine 4x. And y double prime is minus 16 c1 sine 4x minus 16 c2 cosine 4x. And we want 1 of that guy and 16 of this guy, and when we get done, we want to have 0. Okay, so 16 times c1 minus 16 times c1, those guys go away. 16 c2 minus 16 c2, those guys go away. Check. In fact, that is a solution. And number 22, doing the same thing. We're checking to see that we have a solution. Y double prime plus 2y prime plus y is equal to 0, and we want to check that if y is e to the minus x, that is a solution. Okay, so y prime is minus e to the minus x, and y double prime is e to the minus x. and I want one of these guys, two of those guys, and one of these guys, and I'm supposed to get 0 when I get done. Okay, so I got 1 e to the minus x, I got another 1 e to the minus x, and then I got minus 2. Those guys all go away. Check it. It is a solution. All right. So section 1 had to deal with, can you tell the difference between an order and a degree? And if you're given a solution, can you check it? Now, the thing about differential equations is when you get an answer, you don't know that it's right. A lot of your math things that you do, you get an answer and you have some gut feel that it's right. So I have something that says x plus 2 is equal to 4, and you say x is equal to 2. Would you check that? No, because you have a gut feel that it's right. Okay, so and so that's what we're talking about. In a differential equation, when you get your answer, the only way you can know that it's right is if you check it. You have to put it back in. There's no way you can look at it and say, yeah, that makes sense, because it doesn't. So, and it won't. All right. So now we're going to go to section 29.2, and we're going to solve problems by separation of variables. So I've got y prime, I have dy dx, I have dy. All those things mean the same thing. They all mean the derivative of y. They all mean the same thing. Well, what we're doing in this chapter is we're saying, well, this is one thing, right? Y prime, that's one thing, dy. But this guy's two things. So if I have dy dx is equal to 1, I could rewrite that as dy is equal to dx, and then I could integrate both sides, and I could say y is equal to x plus some constant c. And what's dy dx? Dy dx is the slope of the curve, right? And here's I have a straight line with a slope of 1. Dy dx is 1. That's sort of what it says there. And so that it goes back into your the standard form of the equation of a line. All right, so that's all we're doing. We're just going to separate our variables and integrate both sides and hope for the best. Let's see, was there something weird going on there? Oh, there is. Wonder why they had that weirdness sitting there. Anyway, we'll see if we can solve any of these guys. All right, so we'll do 29.2 and call it a day, unless we have lots of time left over, which we might. Number 4. I've got secant x dy is equal to cosecant y dx, and no, it's not. It's equal to 0. There's a plus sign there. So if I write the problem down right, I'd be okay. All right. So what I'll do is I'll keep. What I'm trying to do is get all the things dealing with x on one side of the equation, and all the things dealing with y on the other side of the equation. So I'll do that first. I'll put that on the other side, and then I'll say minus dy over cosecant y is equal to dx over secant. Oh, it's getting late. Secant x. And then I say, well, I'm going to integrate both sides, right? Well, probably not. What's 1 over cosecant? That's integral minus sine y dy. And 1 over secant is cosine x dx. Oh, that's all right. So the integral of sine is minus cosine, and I got a minus there, so this is going to be cosine y is equal to the integral of cosine is sine, so it'd be sine x plus c. Now, we have to have a constant of integration thrown in, but we don't put it on both sides of the equation because whatever it is here, it can be over there, and they don't cancel them out. So I put the c with the x, constant integration with the x guy. And then I say y is equal to the arc secant, the arc cosine. I don't know if I can spell arc cosine. Arc cosine of sine x plus c. And because we want to check our work, this problem number 6? 4. 4? Oh, problem number 4. 28, 28. 29.2, number 4, isn't there. Stupid author, anyway. All right, well, we'll assume that it's right because I couldn't do anything wrong on that one. Numbers, I knew not to check an even one. Number 7. And so dy dx is equal to x squared plus x squared y squared. Okay, so I'm going to go dy dx is equal to x squared times 1 plus y squared. And then I'm going to put the x's on one side and the y's on the other side. dy over 1 plus y squared is equal to x squared dx. I'm going to integrate both sides. And on this side I'm going to have x cubed over 3 plus c. Now what is the integral of 1 over y squared dy? One would think that I'd have that memorized, and I'm pretty sure that's the integral of 1 over 1 plus that. It's going to be, oh, wait a minute, 1 over that, arc tangent. Okay, so it's going to be arc tangent y. Tangent y is equal to that. So y is going to be the tangent of x cubed over 3 plus c. And that we can check because that was number 7. And number 7 says arctangent y is equal to x cubed over 3 plus c. Well, they left it in this form, and didn't, so they left the answer like that, which is perfectly okay. I can leave the answer like that too if I wanted to. Number 19, good. Another odd one, just in case I get it wrong. Thank you very much, Mr. Cordoville, for assigning such things. Oh, look at that! What a pain. dy dx equals 1 plus x squared plus y squared plus x squared y squared. Good thing we did Tech Math 2, otherwise we wouldn't be able to factor this, right? Alright, if I had x squared plus 1 times y squared plus 1, I'd have x squared, y squared, I'd have an x squared, I'd have a y squared, and I'd have a 1. Oh, good, excellent. Now I can separate my variables. dy over y squared plus 1 is equal to x squared plus 1 dx. Integrate both sides. We already said that this guy over here is arctangent. Arctangent y is equal to x cubed over 3 plus x plus c. And I would imagine that that's what the back of the book has for 19. And I'd be very disappointed if it didn't. Well, they have it in a different order. They put the x first and the x cubed over 3 second. But that checks with back of the book. Okay, one more. What are we doing? 30? Number 30. Okay, this time we're given an initial condition, so not only do we have to solve the differential equation, but then we have to figure out what C is. Alright, so I've got x squared dy is equal to y dx. And I have y at 1 is 1. Okay, so that's the problem that I have. Okay, so I got dy over y is equal to dx over x squared. I'm going to integrate both sides. I have natural log y is equal to 1 over x minus 1 over x plus c. Right? If I take the derivative of this, if that was x to the minus 1, I take the derivative, minus 1 goes on plus, make it positive, subtract 1 makes it a 2. Alright, so I've got, I'm going to raise as powers of e, and I get y is equal to c, e to the minus 1 over x. Okay, now I'm going to apply my initial condition that says y at 1 is 1. Okay, so y at 1, which is 1, is going to be c e to the minus 1. Clearly implying that c had better be equal to e, right? C is equal to e.
How's that?
Well, e times 1 over e is 1, so that must be it. So final answer should be y is equal to e to the minus 1 over x, and I'd probably rewrite that as e to the 1 minus 1 over x, right? I rewrite it like that. Oh, good. This is e odd, so I can't possibly know what the right answer is. But I could put it in Maple. So in Maple, tools, assistance, ordinary differential equation solver. So I've got we want the first derivative, right? Okay. So we want y with respect to x. First derivative. Insert. And then we just want a y. Yeah, we just want a y. So insert. Alright, so I'm going to rewrite it to say dy dx is equal to y of x divided by x squared. Okay, I think that's the problem we have. Okay, so dy dx is equal to y divided by x squared. Alright, so that's done. And then we have an initial condition, and it says y at 1 is 1. Y at, oh, we already got it. Y at 1 is 1. Alright, that's done. What are you complaining about? Solve. Boom. Solve. Boom. There we go. That looks like my answer. Does that look like my answer? Yeah. Yeah, it looks like my answer. Stupid guys. Why couldn't you write it like my answer? But yeah, that looks like my answer.
Because the computer is not as smart as you.
The computer is supposed to be the power of 1,000 mathematicians, and so I better be smarter than I am, otherwise we're in real trouble.
It's only as smart as what you put into it.
That's right, that's the problem with it. Okay, I guess 29. We can hold off on 29.3 until next time. Let me do a Control Alt F12.